What if everything you see around you, the stars above, the ground beneath your feet, even the air you breathe, is just the surface of something far more intricate, something hiding in plain sight? The universe has always been full of mysteries, but some of its deepest secrets might not be in distant galaxies or black holes. They could be woven into the very fabric of reality itself, structures so strange and subtle that we're only just beginning to glimpse their shadows. Have you ever stared up at the night sky and felt that tug of curiosity, that whisper in the back of your mind asking, what if there's more? For centuries, humans have tried to peel back the layers of the cosmos, uncovering one astonishing truth after another. From the dance of planets around the sun to the mind-bending twists of spacetime, every discovery has revealed just how little we truly know. But now, scientists are probing even deeper, chasing clues that suggest our universe might be built on hidden frameworks, structures so bizarre they defy our everyday intuition. Think of it like an iceberg. The reality we perceive, that's just the tip. Beneath it lies a vast, uncharted depth of possibilities, from cosmic strings stretching across the void to dimensions folded so tightly they're invisible to our eyes. This isn't just science fiction. These are real theories backed by equations and observations, proposed by brilliant minds daring to ask the biggest questions. Some of these ideas might sound impossible, even unsettling, like the notion that our entire universe is a hologram, or that countless parallel realities exist just out of reach. Others hint at a cosmic architecture so elegant it could rewrite physics as we know it. But here's the most thrilling part. We're living in an era where these theories aren't just fantasies. They're puzzles waiting to be solved, and every new telescope, every particle collider brings us closer to the answers. So if you've ever wondered what lies beyond the edge of our understanding, you're in the right place. Buckle up, we're about to dive into the 30 most fascinating theories about the universe's hidden structures, and trust me, you won't look at reality the same way again. Picture a hologram on your credit card, that tiny, shimmering image that shifts as you tilt it. From one angle, it looks flat, just an ordinary sticker. But tilt it slightly, and suddenly it pops into 3 dimensions full of depth and movement. Now, what if our entire universe works the same way? That's the mind-bending idea behind the holographic principle, a theory suggesting that everything we experience, the stars, the planets, even you and me, might just be a 3-dimensional projection of information encoded on a distant 2-dimensional surface. This isn't just wild speculation. The idea traces back to black holes, those cosmic enigmas where gravity is so intense that not even light can escape. In the 1970s, physicist Jacob Bekenstein discovered something astonishing. The amount of information a black hole can hold isn't determined by its volume but by its surface area. That's like saying the contents of a thick book aren't stored inside its pages but written entirely on the cover. Decades later, Leonard Susskind and Gerard T. Hooft took this further, proposing that if black holes encode reality on their boundaries, maybe the entire universe does too. Think of it like a movie projected onto a screen. The images appear to have depth, movement, even emotion, but in reality, they're just patterns of light on a flat surface. If the holographic principle is correct, our universe might be an illusion of sorts, a grand cosmic show where the real data exists on some unimaginably distant boundary we can't see. Why would scientists take such a bizarre idea seriously? For one, it solves a major puzzle in physics: how to reconcile Einstein's theory of gravity with quantum mechanics. The holographic principle suggests that gravity isn't a fundamental force at all, it's just a side effect of information playing out on this deeper, 2-dimensional layer. And if that's true, it could rewrite our understanding of reality itself. Skeptics argue it sounds like science fiction, but the math checks out. Experiments using powerful particle accelerators are even searching for subtle pixelation in spacetime, tiny, holographic glitches that might reveal the universe's true, flat nature. So next time you look at a hologram, ask yourself, could reality itself be just as fluid, just as illusory? If so, what else might be hiding in the unseen layers of existence? Now, let's stretch our imaginations even further. Picture threads thinner than an atom but longer than entire galaxies, ribbons of pure energy left behind from the violent birth of the universe. These aren't just cosmic leftovers, they're called cosmic strings, and if they exist, they could be weaving invisible patterns through the fabric of reality itself. Think of the early universe like a block of hot, molten metal cooling rapidly. As it solidifies, tiny cracks and imperfections form in its structure. Cosmic strings might be the same kind of defect, but etched into spacetime during the Big Bang's explosive expansion. Unlike black holes or dark matter, these strings wouldn't be made of matter or energy as we know them. They'd be flaws in the very geometry of the cosmos, regions where space and time are twisted so tightly that a single inch of string could weigh more than Mount Everest. Their effects would be as dramatic as they are subtle. A cosmic string drifting through space wouldn't just bend light like a lens. It would slice through the universe like a taut wire through soft cheese, creating double images of distant galaxies or distorting the microwave glow left over from the Big Bang. Some scientists even speculate that these strings could have acted as cosmic scaffolding, guiding the formation of galaxies by tugging matter into dense clusters over billions of years. Here's where it gets wilder. If two cosmic strings crossed or snapped, they might unleash bursts of gravitational waves, ripples in space-time so powerful they could shake the entire universe. Some researchers are scanning the skies for these faint echoes, hoping to catch a whisper from the universe's infancy. And while no definitive proof of cosmic strings exists yet, their fingerprints might already be hiding in plain sight. Unexplained kinks in the cosmic microwave background, strange alignments of distant quasars, these could all be clues waiting to be deciphered. So why does any of this matter? Because cosmic strings are relics from the first moments of existence. Finding them would be like uncovering the universe's baby photos, a glimpse into a time before atoms, before light, when reality itself was still taking shape. And if they're out there, threaded through the darkness, they could rewrite not just our understanding of the cosmos, but of how everything, including us, came to be. What if every choice you've ever made, every path taken or left behind, exists somewhere out there in the cosmos, playing out in endless variations? That's the startling promise of the Level 1 multiverse, a concept so vast it redefines the meaning of reality. According to this theory, our observable universe, with all its galaxies and stars, might just be one tiny bubble in an infinite cosmic froth. Beyond the limits of what we can see, space stretches forever, and with it the possibilities. This idea springs from a simple but profound truth. If the universe is infinite and matter is distributed roughly evenly, then every possible arrangement of particles must repeat eventually. Picture flipping a coin an infinite number of times. At some point, you'll get a streak of 1,000 heads in a row. Now apply that to reality. Somewhere out there, another Earth orbits another sun, where another version of you chose coffee instead of tea this morning. Another where you became an astronaut, or where dinosaurs never went extinct. The differences could be tiny or colossal, but statistically, they're inevitable. The math behind this comes from inflationary cosmology, which suggests the universe expanded exponentially in its first moments. This rapid stretching didn't just create the cosmos we know, it created pockets of space so distant from each other that light from one could never reach the other, even given infinite time. Each of these pockets becomes its own observable universe with its own unique history. And because quantum fluctuations during inflation sprinkled matter randomly, no two pockets are exactly alike. But here's where it gets truly surreal. If space is truly infinite, there aren't just slight variations of your life, there are exact duplicates. Statistically, an identical copy of you reading this exact sentence exists right now in a galaxy far beyond our cosmic horizon. Every thought, every memory perfectly mirrored, and that's not even the weirdest part. Some versions of you might live in universes where the laws of physics are subtly different, where gravity is stronger or light moves slower. Critics argue this theory is untestable, a philosophical thought experiment rather than hard science. But supporters counter that it's the natural consequence of our best cosmological models. If inflation happened, and the evidence says it did, and if space is infinite, as measurements suggest, then the level 1 multiverse isn't just plausible. It's unavoidable, so the next time you second-guess a decision, remember, somewhere out there, another you did things differently, and who's to say which path is the right one? In an infinite cosmos, every possibility is not just imaginable, it's inevitable. If the level 1 multiverse stretched your mind, hold on, because level 2 plunges us into something even stranger. Imagine space isn't just infinite, it's bubbling. Not with soap suds, but with entire universes, each hidden inside its own cosmic pocket, governed by entirely different laws of physics. This is the level 2 multiverse, where reality isn't just varied, it's rewritten. The key to this idea lies in a process called eternal inflation. Picture the early universe as a pot of water on the verge of boiling. Most of space remains calm, but every so often, a bubble forms a sudden, violent expansion where the fabric of reality stretches exponentially. In our universe's case, one of these bubbles inflated into everything we know: galaxies, planets, life. But here's the twist. Outside our bubble, the boiling hasn't stopped. Countless other universes keep sprouting, each with its own unique physics. Some might have stronger gravity, making stars burn out in seconds. Others could have no gravity at all, just a formless soup of particles. What fuels this endless bubbling? Vacuum energy, a mysterious force lurking in empty space. In some regions, this energy might drop suddenly, like a ball rolling downhill, triggering a new inflation bubble. But in others, it lingers, keeping space stretched thin and ripe for more universes to emerge. It's a cosmic lottery where every bubble gets a random set of rules. Now, here's where things get even wilder. These bubble universes might not stay forever separate. If two bubbles collide, the shockwave could ripple through both, leaving scars in the cosmic microwave background, the afterglow of the Big Bang. Scientists have actually searched for these telltale bruises, faint circles or asymmetries in the sky that could be echoes of a long-ago cosmic crash. Critics argue we'll never observe another bubble universe directly, but supporters counter that their existence solves one of physics' biggest mysteries: why our universe seems so finely tuned for life. If infinite bubbles exist with infinite possible laws, statistically, some had to get lucky. We're just living in one of the lucky ones, so the next time you gaze at the night sky, remember, it might not just be stars looking back. Somewhere beyond the edge of our cosmic bubble, another universe could be unfolding, utterly alien, yet born from the same primordial chaos. And if we ever find its fingerprints in the heavens, it would prove we're not just part of a multiverse, we're part of something far grander, a cosmic tapestry still weaving itself into existence. Now let's venture into a multiverse even closer to home, one that doesn't sprawl across infinite space or bubble from cosmic inflation, but branches from the very choices we make. This is the Level 3 multiverse, born not from cosmology but from quantum mechanics, and it's perhaps the most personal multiverse of all. Imagine every time you faced a decision whether to turn left or right, to speak up or stay silent. The universe didn't just follow one path. It split, creating two parallel realities where both outcomes play out. That's the radical vision of the many worlds interpretation, where reality isn't a single thread but an endlessly dividing tapestry of possibilities. The idea traces back to the strange behavior of quantum particles, those tiny building blocks of reality that seem to defy logic. In experiments, particles exist in a haze of probabilities, like a coin spinning in midair, neither heads nor tails until it lands. Traditional physics says this superposition collapses into one outcome when observed, but the many worlds interpretation argues something far wilder. Every possible outcome does happen, just in separate, branching universes. The moment you look at that quantum coin, reality fractures, one world where it's heads, another where it's tails. This isn't just about particle physics. Apply it to everyday life, and the implications are staggering. A universe where you took that job offer exists alongside one where you didn't. A world where dinosaurs still roam might branch from a single quantum event millions of years ago. Unlike Level 1's distant copies or Level 2's alien physics, these parallel realities are woven from the same quantum fabric as our own, diverging silently at every turn. So why can't we see these other worlds? The answer lies in quantum decoherence, a process that makes branching universes invisible to one another. Think of it like tuning a radio. Each station broadcasts simultaneously, but you only hear the one you're dialed into. In the quantum multiverse, every reality vibrates at its own frequency, its signals fading into noise before they can interfere. This isn't just theory. Scientists have observed decoherence in labs, watching quantum possibilities leak away as they entangle with their environment. Critics argue that the many worlds interpretation is untestable by nature. If we can't interact with parallel worlds, how can we prove they exist? Yet supporters point to quantum computing, where particles harness parallel states to solve problems exponentially faster. If a quantum chip can explore multiple paths at once, they ask, why couldn't the universe? Whether or not the Level 3 multiverse is real, it challenges our deepest assumptions about choice and destiny. Every decision, no matter how small, might send ripples through the quantum foam, spinning off worlds where our luck, our love, even our laws of physics unfold differently. So the next time you hesitate at a crossroads, remember, some version of you didn't, and in another reality, that might make all the difference. If the first 3 levels of the multiverse stretched your imagination, Level 4 will snap it entirely. This is where we leave behind the familiar, no branching timelines, no bubbling universes, and step into a realm where every mathematically possible structure, no matter how bizarre, exists as its own independent reality. Proposed by physicist Max Tegmark, this isn't just a theory about other versions of our universe. It's the claim that every equation scribbled on a chalkboard, every geometric shape, every conceivable pattern of existence, from a universe made entirely of fractals to one where time flows backward, is out there somewhere, physically real. Think of mathematics not as a human invention, but as the fundamental fabric of reality. The number pi doesn't just describe circles, it is a circle somewhere in the Level 4 multiverse. A universe where gravity follows an inverse cube law instead of an inverse square. It's not just a thought experiment, it's a place. Even worlds with no connection to our physics, where dimensions multiply endlessly or causality unravels into nonsense, would exist simply because they can be described mathematically. This idea forces us to confront a profound question. What does it mean for something to exist in our daily lives? We equate existence with what we can see, touch, or measure. But Tegmark argues that abstract mathematical structures are just as real. They're not invented but discovered, like uncovering continents on a cosmic map. If a universe can be described by consistent equations, then in some sense it must be out there waiting. Critics push back hard, calling Level 4 less a scientific theory and more a philosophical stance. After all, if every possible universe exists, how could we ever test it? Science thrives on falsifiability, the ability to prove ideas wrong, but Level 4 seems to swallow all possibilities, leaving no room for contradiction. Even Tegmark admits it's more of a metaphysical rabbit hole than a hypothesis with experimental evidence. Yet supporters counter that this might be the ultimate form of Occam's razor, the principle that the simplest explanation is often best. Instead of asking why our universe has precisely the right constants for life, Level 4 answers because all possible constants exist. No fine-tuning, no lucky accidents, just an infinite landscape where every permutation plays out. The debate touches something deeper than physics. It's about the nature of reality itself. Are we living in a universe that's one rare, special fluke? Or are we just one page in a library so vast it contains every story that could ever be written? For now, Level 4 remains at the edge of scientific respectability, too wild to prove, too compelling to ignore. But if it's true, then the most exotic worlds we can dream up aren't fiction. They're just waiting out there in the cosmic archive of all possible things. Imagine the entire universe in motion, not just stars orbiting galaxies or galaxies drifting apart, but something far stranger. Hundreds of galaxy clusters, each containing thousands of galaxies, all streaming in the same direction at breathtaking speeds, as if dragged by some invisible current. This isn't science fiction, it's a real, observed phenomenon called dark flow, and it defies everything we know about cosmic motion. The story begins with the cosmic microwave background, the faint afterglow of the Big Bang. Scientists use this ancient light like a cosmic speedometer, measuring how galaxy clusters move relative to its uniform glow. But in 2008, researchers analyzing data from the Wilkinson Microwave Anisotropy probe noticed something unsettling. Over 1,000 galaxy clusters weren't just drifting randomly, they were all hurtling toward the same patch of sky at speeds exceeding 2 million miles per hour. Even more bizarre, this motion couldn't be explained by the gravitational pull of any known structure in our universe. The leading theory is as radical as the observation itself. Beyond the observable universe, there might be regions of space-time so massive, perhaps even other universes, that their gravity tugs on our galaxy clusters like a cosmic magnet. Picture standing on a beach, feeling the tide pull at your feet, yet the ocean itself is hidden beyond the horizon. That's the eerie implication of dark flow. We're sensing the gravitational echo of something outside our cosmic bubble. Not everyone's convinced. Skeptics argue it could be a measurement error or an undiscovered local structure warping our view. After all, the observable universe stretches 93 billion light-years across. Couldn't there be colossal superclusters just beyond our sight? But here's the catch. Even the most massive structures we know shouldn't generate this kind of coordinated motion. The scale is all wrong. Then there's the wildcard possibility. Dark flow might be a relic from before the Big Bang. Some models of cyclic cosmology suggest our universe is one in a chain, with each birth preceded by a previous collapse. If true, the imprint of that earlier epoch could still linger, dragging matter in its wake like shadows of a forgotten age. Whatever the explanation, dark flow challenges the very notion of cosmic isolation. If confirmed, it would mean our universe isn't just one among many, it's actively entangled with realms beyond our vision. And that raises an even deeper question. If the cosmos is pulling us toward something unseen, what else might be out there waiting to rewrite the story of everything? The Big Bang has long been the reigning origin story of our universe, a singular explosion of energy and space bursting into existence from nothing. But what if that wasn't the beginning? What if our universe is trapped in an endless cosmic heartbeat, expanding and collapsing over and over, like a phoenix perpetually reborn from its own ashes? This is the mind-bending premise of the Big Bounce, a theory that rewrites the destiny of everything. Instead of a one-time Big Bang, the Big Bounce suggests our universe cycles through phases of expansion and contraction. Picture a rubber band stretched to its limit. Instead of snapping, it recoils. Now imagine that rubber band is space-time itself. In this model, each big crunch doesn't end in oblivion. Quantum effects like a cosmic safety net might prevent matter from collapsing into a singularity, instead triggering a rebound, a new Big Bang, and with it a fresh universe. This idea solves one of cosmology's biggest puzzles. What came before the Big Bang? A bouncing universe has no true beginning, just an eternal loop where each cycle inherits traces of the last. Some versions of the theory even suggest subtle fingerprints from past universes might linger in the cosmic microwave background, like echoes of a forgotten age. Quantum gravity lies at the heart of this resilience, near the crunch point where gravity would normally crush everything into infinite density. Quantum mechanics could step in. The uncertainty principle might create a repulsive force, like a trampoline at the bottom of a fall, bouncing space-time outward again. It's a cosmic reset button, wiping the slate clean while preserving the underlying rules. But the big bounce isn't without its critics. Some argue that dark energy, the mysterious force accelerating our universe's expansion, might prevent a future collapse, dooming the cosmos to an icy, endless drift. Others question whether quantum gravity, still an unproven framework, can truly salvage a contracting universe from annihilation, yet the theory's elegance keeps it alive. It offers a universe without edges, without absolute death, just an endless dance of creation and renewal. If true, our cosmos might be just one chapter in an epic with no first page, no final line. And that raises a haunting question. If universes can rise from their own collapse, how many times has this story already been told? What if the Big Bang wasn't a bang at all, but a crash? Imagine two colossal sheets of reality floating like phantom sails in a higher dimensional void, drifting closer until collision. The energy of that impact didn't just make a sound, it birthed an entire universe. This is the daring vision of the ekpyrotic universe, a theory that swaps cosmic fireworks for something far more exotic, a clash of dimensions. At its heart lies the idea of brains short for membranes, borrowed from string theory's wildest playground. In this framework, our three-dimensional universe might actually be a vast floating brain, one of many adrift in a hidden, higher dimensional space. Picture a soap bubble suspended in air, its surface thin but stretching endlessly. Now imagine another bubble floating parallel to it. If these two bubbles grazed or collided, the energy released wouldn't just ripple, it could ignite an entire cosmos. That's the ekpyrotic scenario. Our universe wasn't born from nothingness, but from the explosive meeting of two titanic brains. This idea solves one of cosmology's biggest headaches. Why is the universe so uniform? The cosmic microwave background, the afterglow of the Big Bang, reveals a startlingly smooth distribution of matter and energy, as if the entire cosmos had been stirred like cream in coffee. Traditional inflation theory explains this by proposing a fleeting period of hyper-expansion, stretching wrinkles flat. But the ekpyrotic model offers an alternative. Those two colliding brains were already stretched smooth before impact, like sheets of glass pressed together. The collision didn't create chaos, it transferred that pristine order into our newborn universe. Critics pounce on a glaring question: where's the evidence? Unlike cosmic inflation, which predicts faint gravitational waves imprinted on the cosmic microwave background, the ekpyrotic model leaves subtler fingerprints. Some versions suggest rare, donut-shaped voids in the universe's structure. So far, none have been found. Others argue the theory relies too heavily on unproven string theory math, trading one mystery for another. Yet supporters counter that the ekpyrotic universe elegantly sidesteps inflation's own puzzles, like what triggered it, or why it stopped, and if brains do exist, their collisions might not be one-time events. Our universe could be caught in an endless cycle of brain crashes, each resetting the cosmic clock. That means the Big Bang wasn't the beginning, just the latest chapter in an eternal saga of collisions and rebirth. So while we wait for proof, the ekpyrotic universe stands as a bold reminder. Sometimes the most extraordinary answers lie not in the void, but in the echoes of a long-forgotten collision. What if everything you've ever experienced, every sunrise, every heartbeat, every whispered conversation, was nothing more than lines of code in an unfathomably advanced simulation? This isn't just the plot of a sci-fi movie. It's a serious philosophical argument, one that forces us to confront three unsettling possibilities about the nature of reality. The simulation argument, proposed by philosopher Nick Bostrom, presents a trilemma: three options, all equally staggering. Option 1. Nearly all civilizations at our level of technological development eventually go extinct before reaching a post-human stage capable of creating universe-scale simulations. Option 2. If civilizations do survive, they almost never choose to run ancestor simulations, digital recreations of their past. And Option 3. We're almost certainly living inside one of those simulations right now. Bostrom's math suggests these are the only plausible outcomes, and if the first two seem unlikely, the third becomes disturbingly probable. Think of it like this. Imagine a future where computing power is limitless and post-human beings decide to simulate their evolutionary history, just as we might recreate ancient Rome in a video game today. They could run countless simulations, each with self-aware digital beings who believe their world is real. Statistically, the number of simulated minds would dwarf the number of original biological ones. So if you're a conscious being, the odds overwhelmingly favor you being one of the simulated ones. This idea isn't just philosophy, it's entangled with the Fermi paradox, the eerie silence of the cosmos. If intelligent life is common, where is everyone? One chilling answer: advanced civilizations don't explore the stars because they're too busy simulating realities inside supercomputers. The universe might be empty not because life is rare, but because everyone's plugged into a cosmic VR headset. But how could we ever know? Some scientists suggest looking for glitches or tiny errors in the fabric of reality that might betray the simulation's underlying code. Maybe the universe has a pixelation limit, like a video game where zooming in far enough reveals jagged edges. Others propose that anomalies in quantum mechanics, like particles existing in multiple states until observed, could be processing shortcuts, the simulation conserving resources by only rendering what's being watched. Of course, skeptics dismiss this as modern-day solipsism, a high-tech version of "how do I know the world exists?" But the simulation argument isn't claiming we are in a simulation, just that, given certain assumptions, the probability is shockingly high. And if it's true, it rewrites the meaning of existence itself. Your joys, your sorrows, the vastness of the cosmos, all might just be data in some unfathomable machine. So here's the real question. If reality is a simulation, does that make it any less real to the ones living inside it? After all, even lines of code can create a universe worth exploring. And if we're part of someone else's experiment, maybe the greatest discovery isn't breaking out but figuring out what we're meant to learn. Black holes have long been the universe's ultimate enigma, cosmic traps where gravity wins so decisively that even light can't escape. But what if these terrifying voids aren't just destructive? What if, hidden beyond their event horizons, they contain entire universes of their own? This is the radical premise of the black hole universe theory, an idea that flips our understanding of these monsters on its head. Instead of being dead ends, black holes might be cosmic wombs, birthing new realities with every collapse. Let's start with the singularity, the infamous point at the heart of a black hole where gravity crushes matter into infinite density. Traditional physics breaks down here, equations spitting out nonsense. But what if the singularity isn't a true endpoint? Some theories suggest that as matter collapses, extreme quantum effects could twist spacetime so violently that it rebounds, exploding outward in a new Big Bang. Picture a dying star not vanishing into oblivion, but becoming the seed for a fresh universe, hidden behind the veil of an event horizon. Our own cosmos, then, might owe its existence to a black hole in some higher dimensional parent universe. This idea isn't just poetic, it solves real problems. For one, it sidesteps the singularity's paradoxes by replacing infinity with a transition. It also dovetails eerily with the holographic principle. If a black hole's information is encoded on its surface, perhaps the universe inside is just a projection of that data, like a cosmic Matryoshka doll where each layer encodes the next. Supporters point to the math. Equations describing a collapsing star and an expanding universe are hauntingly similar, almost mirror images. Even stranger, the entropy of a black hole, a measure of its hidden information, matches predictions for the early universe's disorder. It's as if the universe carries a fingerprint of its birth encoded in its chaos. But how could we ever test this? Some scientists propose looking for quantum imprints in the cosmic microwave background, subtle anomalies that might betray our universe's black hole origins. Others suggest that the way galaxies cluster could echo the structure of a parent black hole's event horizon. Of course, skeptics argue this is speculative metaphysics, not testable science. Yet the theory's elegance lingers. If true, every black hole in our universe might contain a cosmos as vast and rich as our own, each with its own black holes, each birthing new realities in turn. It's a dizzying vision, not just a multiverse, but an infinite nesting of universes, each hidden behind the unlit doorway of a singularity. And that raises a haunting question: if we're inside a black hole, what lies beyond our event horizon? Time crystals sound like something ripped straight from the pages of a fantasy novel. Structures that pulse and oscillate forever, never winding down, never needing fuel. Yet these bizarre quantum systems are very real, and they challenge everything we thought we knew about the fundamental nature of time and energy. Unlike ordinary crystals, where atoms arrange themselves in repeating patterns in space, time crystals arrange themselves in repeating patterns in time. Imagine a clock that ticks perfectly, endlessly, without ever being wound. A perpetual motion machine that defies the most sacred law of physics, entropy. The idea was first proposed by Nobel laureate Frank Wilczek in 2012, met with both fascination and skepticism. Classical thermodynamics insists that everything degrades, that energy dissipates, and that perpetual motion is impossible. Time crystals don't break these rules, they sidestep them entirely. By existing in a quantum system tuned to a precise, lowest energy state, they achieve something extraordinary: periodic motion that doesn't require energy input. Picture a ring of atoms that flips its spin configuration every few moments, like a cosmic metronome ticking in perfect rhythm forever. It's not creating energy, it's dancing in place, locked in a loop that time itself can't disrupt. What makes this even stranger is how they form. Traditional crystals, like diamonds or snowflakes, emerge when a system cools and settles into equilibrium. Time crystals, however, only appear out of equilibrium. They're born from systems constantly nudged by external forces, yet somehow settling into a rhythm more precise than a Swiss watch. Scientists have actually created them in labs using chains of ions or diamond defects, observing their eerie ticking firsthand. But why does this matter beyond the lab? For one, time crystals might be hiding in plain sight as dark matter. Some theories suggest these structures could have formed in the early universe, their stable, repetitive nature making them perfect candidates for the invisible mass shaping galaxies. Others propose they could act as cosmic sensors. Because their oscillations are exquisitely sensitive to disturbances, a network of time crystals might detect ripples in spacetime itself, gravitational waves too faint for current observatories to catch. The implications stretch even further. If we can harness their properties, time crystals could revolutionize quantum computing, creating memory systems immune to decoherence. They might even rewrite our understanding of time's arrow, suggesting that under the right conditions, the universe permits structures that tick forward indefinitely, like echoes of order persisting in the chaos. Skeptics caution that time crystals are still in their infancy, more curiosity than application. Yet their existence alone proves something profound. The universe still holds puzzles that defy our oldest assumptions. In a cosmos where even time can crystallize, who knows what other impossibilities might be waiting just beyond the edge of our understanding? The universe is supposed to be isotropic, uniform in all directions, no special axes, no cosmic up or down. But what if we've been wrong? Hidden in the afterglow of the Big Bang, scientists have stumbled upon a pattern so peculiar, so seemingly deliberate, they've dubbed it the axis of evil. This isn't some apocalyptic prophecy, it's a series of eerie alignments in the cosmic microwave background, the oldest light in existence that shouldn't be there. And the strangest part, these anomalies line up uncannily with the plane of our solar system, as if the universe itself is pointing a finger straight at us. The story begins with the Wilkinson Microwave Anisotropy Probe, a satellite designed to map the cosmic microwave background with unprecedented precision. The CMB is the universe's baby picture, a snapshot of its fiery infancy, frozen in time. Tiny fluctuations in this ancient light reveal the seeds of galaxies, the whisper of quantum noise stretched across the cosmos. But when researchers analyzed the data, they noticed something unsettling. The largest scale fluctuations, those spanning billions of light years, weren't random. They were oddly aligned, forming a pattern that seemed to trace an invisible axis. And when they plotted this axis, it pointed eerily close to the plane of our own solar system. At first, scientists assumed it was a fluke, an artifact of measurement or processing. But as newer missions like Planck confirmed the alignment, the discomfort grew. The odds of this happening by chance, less than 1 in 1,000. It's like rolling a die 100 times and always getting a 4, something's clearly off. So what could explain it? One possibility is contamination. Our own galaxy's dust or the solar system's motion might be skewing the data, but meticulously removing these effects barely nudges the anomaly. Another idea invokes new physics, a fundamental asymmetry in the early universe, perhaps leftover from a pre-Big Bang phase where space itself had a preferred direction. Some theorists even suggest this axis could hint at a larger structure beyond our observable universe, a cosmic pull so vast it's tipping the scales of reality itself. The boldest and most controversial interpretation, that we're seeing evidence of a privileged frame, a slice of the cosmos where the rules are subtly different. Einstein's relativity insists no such frame should exist, but if the axis of evil holds up, it might force us to rewrite the textbooks. Skeptics argue it's premature to toss out centuries of physics. Maybe the anomaly is a statistical mirage or a quirk of how we process the CMB. But until we crack this cosmic riddle, one thing's certain: the universe just got a lot weirder, and it's pointing right at us. Somewhere beyond the veil of the Milky Way, hidden behind thick curtains of cosmic dust and stars, lurks a mystery so massive it's pulling entire galaxies toward it at breakneck speeds. This is the Great Attractor, a gravitational monster so powerful it warps the motion of hundreds of thousands of galaxies, including our own. Imagine a cosmic whirlpool, its currents dragging everything nearby into its unseen depths. But here's the catch: we can't actually see it. The discovery began in the 1970s when astronomers noticed something odd about the Milky Way's motion. Even after accounting for the expansion of the universe, our galaxy, along with the entire local group, was racing toward the constellation Centaurus at over 1 million miles per hour. But when they looked in that direction, the view was blocked by the Milky Way's own galactic plane, a region so choked with gas and dust it's called the zone of avoidance. Whatever was pulling us lay beyond it, invisible to traditional telescopes. Early guesses pointed to a colossal supercluster, a gathering of galaxies so massive its gravity could bend the paths of entire galactic neighborhoods. And sure enough, once infrared and radio telescopes pierced the cosmic fog, they found evidence of the Norma cluster, a dense knot of galaxies about 250 million light-years away. But the math didn't add up. The Norma cluster, while massive, wasn't nearly heavy enough to explain the great attractor's pull. So what was one possibility is dark matter. If the attractor is embedded in an especially dense filament of this invisible substance, its gravity could extend far beyond the visible galaxies, tugging on everything in its reach. But some researchers argue even that might not be enough. The sheer scale of the motion suggests something even grander, like the Shapley supercluster, a staggering collection of galaxies over 4 times farther away, whose combined gravity might be amplifying the effect. Then there's the wildcard theory. The great attractor might not be an object at all, but a ripple in the fabric of spacetime itself. Some models of the early universe predict defects in its structure, cosmic strings or domain walls, that could generate gravitational anomalies without the need for concentrated mass. If true, the great attractor could be less a thing and more a glitch in the cosmic code, a remnant from the universe's earliest moments warping reality around it. So why does this matter? Because the great attractor isn't just pulling galaxies, it's pulling our understanding of the cosmos into uncharted territory. If it's a supercluster, it challenges how we model dark matter's distribution. If it's something stranger, it could rewrite the rules of gravity itself. And as new telescopes peer deeper into the zone of avoidance, one thing's certain: whatever's lurking there, it's far more than we bargained for. The universe, it seems, still has a few surprises up its sleeve. The cosmos stretches across nearly 100 billion light-years, filled with hundreds of billions of galaxies, each home to countless stars and planets. With odds like that, the universe should be teeming with civilizations, so where is everyone? This glaring silence, known as the Fermi paradox, might be more than just a puzzle. It could be a signpost pointing toward hidden structures shaping the fate of all intelligent life. Consider the eerie quiet first noted by physicist Enrico Fermi. Even conservative estimates suggest there should be thousands, if not millions, of advanced civilizations in our galaxy alone. Yet after decades of listening, we've heard nothing. No radio signals, no megastructures, no distant probes. The most unsettling explanation: something is systematically preventing life from reaching the stars or surviving long enough to be heard. This something might not be random. It could be woven into the fabric of reality itself. One chilling possibility is the dark forest theory, inspired by the way predators hide in nature. Imagine a universe where every civilization stays silent, afraid to reveal its location. Why? Because in a cosmos where resources are finite and trust is non-existent, broadcasting your existence might invite annihilation. Advanced societies could be lurking in the shadows, striking down any newcomers before they become a threat. If true, the universe isn't empty, it's a battlefield where survival depends on absolute stealth, and the silence isn't natural, it's engineered. Then there's the great filter, a hypothetical barrier that prevents life from advancing too far. This could be a rare evolutionary step, like the leap from single-celled organisms to complex life, or something more sinister lurking ahead. Perhaps every civilization reaches a point where their technology inevitably destroys them, whether through war, environmental collapse, or mishandling artificial intelligence. The filter might not be behind us, but ahead, a cosmic dead end waiting for any species reckless enough to stumble into it. Or maybe the answer lies in dimensions we can't perceive. Advanced civilizations might have transcended our three-dimensional reality, moving into higher planes where communication with flatlanders like us is impossible. Think of it like ants in a garden, oblivious to humans chatting just feet away. The universe might be buzzing with activity, just not in any form we can detect. The Fermi paradox forces us to confront an uncomfortable truth. The absence of aliens isn't just a curiosity. It could be a warning, a clue etched into the void. Whether the universe is a dark forest, a gauntlet of filters, or a dimensional prison, one thing's clear: we're not just searching for life out there. We're searching for the hidden rules that might decide its fate, and until we understand them, silence might be the only answer we get. Imagine a forest at night, pitch black, silent, every creature holding its breath, afraid to make a sound. Now stretch that image across the cosmos. This is the dark forest hypothesis, a terrifying answer to the Fermi paradox proposed by sci-fi author Liu Cixin, and it suggests the universe isn't empty. It's hiding. The logic is brutally simple. In a forest teeming with predators, any sign of weakness or worse, visibility spells doom. The same could be true for civilizations. If even one advanced species out there sees others as threats, broadcasting your location is suicide. They might strike first, not out of malice but cold calculus, eliminate potential rivals before they grow strong enough to do the same. In this scenario, silence isn't just survival, it's the only rational strategy. This idea reshapes how we see the cosmos. Forget hopeful visions of galactic federations or friendly first contact. The dark forest paints a universe where trust is non-existent, and every civilization is a hunter or prey. It explains why decades of listening have heard nothing. Not because aliens aren't there, but because they've learned not to speak. Even our own radio signals, leaking into space for over a century, might be less a hello and more a target painted on our backs. But could this really be the universe's hidden structure? Some argue it's too pessimistic, that cooperation, not destruction, drives progress. Others counter that evolution itself favors caution. On Earth, life thrives through competition. Why wouldn't the same apply between stars? And if just one civilization adopts the dark forest mindset, the rules are set. The cosmos becomes a game of hide and seek where losing means extinction. There's a darker twist. The hypothesis implies that any civilization reaching a certain technological level faces a choice: stay silent forever or risk annihilation by revealing itself. This could create cosmic dead zones, regions where life briefly flickers before being snuffed out. It's a chilling filter that might explain the great silence. Yet the dark forest isn't just about fear. It hints at something profound about intelligence itself. Maybe the universe could be full of cooperation and wonder, but the stakes are too high to find out. Until someone breaks the silence, we're left with a haunting question. Is the cosmos a community waiting to happen, or a battlefield frozen in stalemate? One thing's certain: if the dark forest is real, our attempts to shout into the void might be the most dangerous experiment humanity's ever run. Dark energy might be the most enigmatic force in the cosmos, an invisible pressure stretching space itself apart, accelerating the universe's expansion at an ever-increasing rate. But what if this mysterious force isn't just gently pushing galaxies away? What if it's growing stronger over time, destined to become so overpowering that it tears apart the very fabric of reality? This nightmare scenario is known as the Big Rip, and it hinges on a particularly vicious form of dark energy called phantom energy, a substance so destructive it could reduce the universe to a sea of fractured, isolated voids. The math behind phantom energy is as unsettling as its implications. Unlike ordinary dark energy, which maintains a constant density as the universe expands, phantom energy increases in strength. Picture a car accelerating downhill, not just rolling but pressing the gas harder with every second. As space stretches, phantom energy's grip tightens, its repulsive force growing without limit. According to some models, this runaway effect could reach a point where not even the bonds holding atoms together can resist it. First, galaxies would be shredded apart, then stars torn from their orbits, planets ripped to dust, and finally, in the last unimaginable moments, protons and neutrons themselves would be vaporized. Spacetime wouldn't just expand, it would shatter, but here's where the story takes a stranger turn. Some theorists suggest the Big Rip might not be the ultimate end. Instead, the catastrophic rupture could leave behind remnant universes, isolated pockets of reality floating in an otherwise featureless void. Think of it like a pane of glass shattering into jagged fragments, each piece its own isolated world, forever separated by an infinite abyss. These remnants might inherit scraps of their parent universe's physics, but with fundamental constants twisted, dimensions crumpled, or even time itself fractured. In some scenarios, these shards could become nurseries for new cosmoses, rebounding with their own big bangs, or they might remain frozen, lifeless relics adrift in nothingness. The evidence for phantom energy is thin but tantalizing. Observations of distant supernovas suggest dark energy's density might not be perfectly constant. It could be very slowly increasing. If true, the universe is already on a trajectory toward the Big Rip, though the end wouldn't come for tens of billions of years. But skeptics argue that phantom energy violates cherished laws of physics, like the null energy condition, which prevents certain cosmic catastrophes. Others counter that our understanding of dark energy is still in its infancy. What seems impossible today might just be tomorrow's breakthrough. One thing's certain: if phantom energy is real, the universe's fate isn't just cold and dark, it's violent and final. And that raises a haunting question. If the cosmos is doomed to tear itself apart, could civilization somehow escape? Some speculate about engineering wormholes to flee into other universes, or manipulating spacetime itself to create survivable bubbles. But in the face of phantom energy's infinite hunger, even these might be futile. The lesson is stark. The universe's hidden structures don't just shape its destiny. They might already have written its epitaph. Picture floating alone in an infinite void, no stars, no planets, just darkness stretching forever. Then, out of nowhere, your consciousness flickers into existence, complete with memories, thoughts, even the sensation of a body you never had. You'd swear you'd lived a full life, but in reality, you're a fleeting accident, a random clump of atoms that briefly arranged itself into self-awareness before dissolving back into chaos. This is the bizarre thought experiment known as the Boltzmann brain, and it forces us to confront a chilling possibility. What if the universe we think we know is just a statistical glitch in an endless sea of disorder? The idea comes from Ludwig Boltzmann, the physicist who helped shape our understanding of entropy, the natural tendency of things to move from order to chaos. But here's the twist. In an infinitely old universe, even the most unlikely events must happen eventually. A deck of cards shuffled enough times will eventually deal a perfect royal flush. And given enough time, atoms bouncing around at random could theoretically arrange themselves into a fully formed, thinking brain, complete with false memories of a past that never existed. In fact, in a truly infinite cosmos, Boltzmann brains should outnumber real, evolved minds like ours by an unimaginable margin. So statistically speaking, the odds that you are a real person in a real universe are vanishingly small. This isn't just a philosophical brain teaser, it's a direct challenge to modern cosmology. If the universe naturally trends toward disorder, why does ours look so structured? Why do we see galaxies, planets, and life instead of just chaos? One answer is the Holographic Principle. We observe order because disorder wouldn't allow observers to exist. But the Boltzmann brain takes this further. If random fluctuations can create self-aware minds without a universe, then our entire cosmic history, the Big Bang, the formation of stars, the rise of life, could be an illusion, a fabricated memory in one of these fleeting, solitary minds. Skeptics argue the Boltzmann brain is a reductio ad absurdum, a logical extreme that exposes flaws in our assumptions. Maybe the universe isn't infinitely old, or maybe quantum gravity prevents such freak fluctuations. Others propose that the mere fact we're having this debate is evidence against it. A Boltzmann brain would likely dissolve before forming coherent thoughts, let alone pondering its own existence. Yet the problem lingers like a ghost in the equations. If we accept that the universe tends toward disorder, how do we explain the overwhelming order we see? Is our cosmos a rare bubble of structure in an otherwise chaotic void? Or are we just fooling ourselves, mistaking randomness for design? The Boltzmann brain doesn't offer answers, it shatters certainty, leaving us to wonder if reality itself is as fragile as a thought that could vanish at any moment. Black holes devour everything: light, matter, even time itself. But what if the universe has an opposite, a cosmic exhaust pipe, violently expelling matter and energy instead of trapping it? Welcome to the mind-bending concept of white holes, the hypothetical twins of black holes, and the startling theory that our entire universe might have burst into existence from one. At first glance, the math of white holes seems simple. Reverse a black hole's equations, and instead of an event horizon that only lets things in, you get one that only lets things out. Matter and energy erupt uncontrollably, as if the universe itself were vomiting. While no white hole has ever been observed, their possibility is etched into Einstein's theory of relativity, meaning they're as mathematically valid as black holes once were before we discovered those. Now take this idea further. The Big Bang, a sudden, incomprehensible explosion of energy, bears an eerie resemblance to a white hole's behavior. Instead of a singularity consuming the cosmos, what if it was one violently birthing it? In this model, our universe isn't the aftermath of a random explosion. It's the deliberate ejection from a white hole in some higher dimensional space, a cosmic reversal of the collapse that forms black holes. Some theories even suggest a startling symmetry. Every black hole in our universe could, in turn, spawn a new cosmos inside it through a white hole. Picture a cosmic Russian nesting doll, where each black hole's singularity pinches off into its own spacetime, creating a fresh universe with its own laws. Our Big Bang might just be the white hole echo of a black hole's death in another reality. But why hasn't anyone spotted a white hole? The answer might lie in their fleeting nature. Unlike black holes, which theoretically last forever, white holes could be catastrophically unstable, exploding violently and vanishing almost instantly. Or they might exist only in regions of spacetime so warped that light from them could never reach us. Some researchers speculate that certain anomalous gamma-ray bursts, brief but unimaginably energetic flashes in the sky, could be white holes flickering into existence and dying just as fast. Critics argue that white holes violate the second law of thermodynamics, spewing order into the cosmos without an obvious energy source. Yet supporters counter that in a multiverse or higher dimensional framework, energy conservation might not apply as we know it. A white hole could simply be the other end of a black hole's wormhole, siphoning energy from another reality entirely. Whether real or just mathematical ghosts, white holes force us to reconsider the universe's origin story. If they exist, the Big Bang wasn't an isolated event. It was part of an endless cycle of cosmic regurgitation, where every singularity becomes a genesis. And that raises a tantalizing question. If universes can be born from white holes, what does that make the one we're living in? Just another link in an infinite chain? Or something far stranger? What if gravity, the force that pins us to the planet and guides the dance of galaxies, isn't a fundamental force at all? What if it's just a side effect, an illusion born from something deeper? That's the radical premise of entropic gravity, a theory that flips Newton and Einstein on their heads by claiming gravity emerges not from mass-bending spacetime, but from chaos itself, from the relentless march of entropy. The idea comes from physicist Eric Verland, who took inspiration from an unlikely place, black holes. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that black holes have entropy, a measure of disorder, and that this entropy is tied to their surface area, not their volume. This hinted at something extraordinary. Information about what's inside a black hole might be encoded on its surface like a cosmic hologram. Verland took this further, proposing that spacetime itself might work the same way. What we perceive as gravity could actually be the universe's way of shuffling information, like a cosmic game of Tetris where the blocks are bits of entropy. Here's how it might work. Picture the universe as a vast network of invisible holographic screens, surfaces where information gets stored and processed. When matter moves near one of these screens, it disturbs the information balance, and the screen responds by pushing back. That push, that's what we feel as gravity. In this view, gravity isn't a force transmitted through spacetime. It's spacetime reacting to keep entropy in check, like a thermostat adjusting to maintain equilibrium. This would explain some of cosmology's biggest headaches. Take dark matter, for example. For decades, we've assumed invisible mass must be lurking in galaxies to explain their rotation speeds. But what if there's no dark matter at all? Verlon's math suggests that entropic gravity naturally produces extra, apparent gravity in regions where entropy gradients are steep, precisely where we think dark matter should be. In other words, dark matter might just be a phantom, a misreading of how entropy shapes spacetime's behavior. Critics argue entropic gravity is still half-baked, lacking the precise predictions that could make or break it. Yet tantalizing clues are emerging. Some galaxies do behave as if they're governed by Verlon's equations, no dark matter required. And if he's right, the implications are staggering. Spacetime wouldn't be a static stage, it'd be a dynamic, constructed thing, built moment by moment from information and chaos. So next time you drop your phone again, consider this: gravity might not be pulling it down. The universe might just be tidying up, shuffling bits of entropy to keep its cosmic ledger balanced. And if that's true, reality itself is far stranger and more alive than we ever imagined. We take the smooth flow of time for granted, seconds melting into minutes, the future becoming the past in a seamless river of moments. But what if time isn't continuous at all? What if, beneath the illusion of the ticking clock, reality is stitched together from tiny, indivisible atoms of causality, each one a fundamental building block of existence? This is the radical vision of causal set theory, where spacetime isn't a smooth fabric but a vast, granular network of events linked by cause and effect. Imagine the universe as an infinite cosmic mosaic, where each tile represents a single, irreducible moment, a point where cause meets consequence. In this view, time isn't an emergent property or a side effect of deeper physics. It's the foundation. Every particle collision, every star's birth, every thought you've ever had is a node in this sprawling web, connected by the immutable rule that nothing happens without something else making it possible. Unlike classical physics, where spacetime is a stage on which events unfold, here the stage is the events. The links between them, the causal relationships, are what create the illusion of a flowing, continuous reality. One of the theory's most startling implications is how it handles singularities, those pesky infinities at the hearts of black holes where Einstein's equations break down. In a smooth spacetime, matter crushed to infinite density is a mathematical catastrophe. But in a causal set, there are no infinities because reality is pixelated. Just as a digital image can't zoom in beyond its pixels, a singularity can't shrink smaller than the fundamental grains of the causal set. It's like replacing a bottomless pit with a staircase. You can descend, but there's always a final step. This granularity might also solve another deep mystery: why time only flows forward. In our everyday experience, cause always precedes effect. A cup shatters because it fell, never the other way around. Causal set theory embeds this arrow of time into the universe's very structure. The atoms of causality aren't just scattered randomly, they're strung together in an unbreakable sequence like beads on a cosmic thread. There's no rewinding the tape because the tape itself is made of irreversible links. But how could we ever test such an abstract idea? Surprisingly, there might be clues hidden in the fabric of spacetime itself. If the universe is pixelated, those pixels could leave fingerprints in high-energy phenomena, perhaps in the way gamma rays travel across billions of light years, or in subtle fluctuations in the cosmic microwave background. Some physicists even speculate that black holes, those cosmic shredders of information, might reveal causal set structure in the way they evaporate over eons. Skeptics argue that the theory is too speculative, lacking the mathematical precision to make concrete predictions. Yet its elegance is undeniable. By treating time as fundamental rather than derivative, causal set theory offers a universe where the past, present, and future aren't just human constructs, they're etched into the bedrock of reality. And if it's right, our smooth, continuous cosmos is just a shimmering mirage, hiding a deeper, more intricate truth beneath. What if the eerie connection between entangled particles, those quantum partners that mirror each other instantly across vast distances, isn't just a quirk of physics, but a hidden stitch in the fabric of spacetime itself? This is the bold claim of the ER=EPR conjecture, a theory so revolutionary it dares to bridge the two most incompatible realms of modern science, Einstein's gravity and the quantum world. At its heart lies a stunning proposition: wormholes, those cosmic shortcuts through spacetime, might be the geometric manifestation of quantum entanglement, weaving the universe together from the smallest scales to the largest. Let's untangle this idea piece by piece. Start with Einstein-Rosen bridges, wormholes born from Einstein's equations, hypothetical tunnels connecting distant regions of spacetime. For decades, they were dismissed as mathematical curiosities, unstable quirks of relativity. Then there's entanglement, dubbed spooky action at a distance by Einstein himself, where particles remain mysteriously linked no matter how far apart they are. The ER=EPR conjecture, proposed by physicists Juan Maldacena and Leonard Susskind, suggests these aren't separate phenomena, they're two sides of the same cosmic coin. Picture two entangled particles, their fates forever intertwined. According to this theory, there's an invisible thread connecting them, not a force, not a signal, but a microscopic wormhole, a spacetime bridge too tiny to traverse yet binding them together. This would mean every quantum handshake, every pair of entangled particles, is secretly a quantum tunnel, threading the universe into a vast, hidden network. Spacetime itself might emerge from these quantum connections like a 3D tapestry woven from a web of invisible stitches. The implications are staggering. If spacetime is built from entanglement, then black holes, those cosmic vacuum cleaners, might be gateways, not dead ends. When matter falls into a black hole, it doesn't vanish. It becomes entangled with the hole's radiation, creating a wormhole link to somewhere else. This could resolve the infamous black hole information paradox, the puzzle of whether information swallowed by a black hole is truly lost. Instead, it might be secretly encoded in the spacetime fabric itself, like a message passed through a hidden tunnel. Critics argue the math is still speculative, a tantalizing guess without experimental proof. Yet the theory's elegance is undeniable. It hints at a universe where the quantum and the cosmic are inseparable, where the bonds between particles might literally shape the geometry of reality. Laboratories are now testing this idea by simulating wormholes in quantum computers, watching for echoes of spacetime's hidden architecture. So next time you hear about entangled particles or wormholes, remember, they might not be separate mysteries. They could be clues to a deeper truth, that the universe isn't just held together by gravity or chance, but by an invisible quantum loom weaving every moment into existence. What if our universe has a mirror twin, a parallel cosmos born from the same Big Bang but hurtling backward in time, its very atoms flipped in the flow of causality? This is the haunting symmetry of the Janus cosmological model, a theory that suggests the Big Bang didn't just create our universe, it birthed two, locked in an eternal dance where one moves forward through time while the other spirals in reverse like an echo from the future. The idea emerges from a puzzle as old as physics itself. Why does antimatter exist? For every particle of matter, electrons, quarks, neutrinos, there's an antimatter counterpart with opposite charge. When they meet, they annihilate in a flash of energy, yet the early universe should have produced equal amounts of both, so where did all the antimatter go? The Janus model proposes a radical answer. It didn't vanish. It became the building blocks of an entire shadow universe, one where time runs backward from our perspective. Picture the Big Bang not as an explosion but as a cosmic fork in the road. At the instant of creation, space-time split into two branches, one expanding forward into what we call the future, the other rewinding into what we'd perceive as the past. In this mirrored realm, antimatter isn't just rare, it's the default. Stars burn with anti-hydrogen, galaxies spin in reverse, and entropy decreases over time like a movie played backward. To observers there, we're the ones living in the inverted world. This isn't just poetic symmetry. The model could explain why we see so little antimatter in our universe. If the Big Bang's energy divided asymmetrically, favoring matter in our timeline and antimatter in its twin, the imbalance would be natural, not a cosmic accident. Even stranger, particles in the Janus universe might not just be time reversed. They could be CPT mirror versions where charge, parity, and time are all flipped. A hydrogen atom, there wouldn't just be antimatter, it'd be a perfect inversion of ours in every possible way. But how could we ever detect a universe moving backward in time? The answer might lie in the faintest whispers of the cosmos neutrinos. These ghostly particles, which barely interact with matter, could be slipping between the two universes. Some physicists speculate that certain neutrino anomalies, like their inexplicably small masses, might betray hints of this hidden twin. Others suggest that gravitational waves, ripples in spacetime itself, could carry echoes of the Janus universe's influence, like vibrations from a tuning fork we can't see. Critics argue the model is untestable by nature. If the twin universe is causally disconnected from ours, forever locked behind the veil of the Big Bang's singularity, it might as well be metaphysical. Yet supporters counter that the math is shockingly elegant. The equations of quantum field theory and general relativity don't care which direction time flows, they're perfectly symmetric. A universe running backward is just as valid as ours, and the Janus model simply gives it a home. Whether real or not, the theory forces us to confront the deepest questions about time's arrow. Why does entropy increase? Why do we remember the past but not the future? The Janus universe suggests these might not be fundamental truths, just local quirks of our cosmic neighborhood. Somewhere beyond the Big Bang's afterglow, another reality might be unfolding in perfect reverse, its inhabitants just as certain their time is the right way. And if that's true, the Big Bang wasn't a beginning. It was a reflection, a cosmic Rorschach test where both interpretations are equally real. What if the universe isn't just something we observe? What if it's something we create? This is the staggering premise of the observer's theory, a radical idea that places consciousness at the center of cosmic architecture. At its core lies a simple but profound question. Does reality exist independently of us, or does it take shape only when we look? The answer might rewrite not just physics, but the very nature of existence itself. Consider the double-slit experiment, one of quantum mechanics' most famous puzzles. When particles like electrons are fired at a barrier with two slits, they behave as waves, creating an interference pattern on the other side, unless you place a detector to observe which slit they pass through. The moment you do, the particles snap into well-defined paths, like actors breaking character when they spot an audience. This observer effect isn't about clumsy measurement. It's as if the particles know they're being watched, changing their behavior to fit expectations. Now scale this up to the cosmic level. If quantum systems remain in hazy superposition until observed, could the entire universe be doing the same? In the observer's model, space-time, matter, even the laws of physics might not be fixed until consciousness interacts with them. It's not that the moon disappears when no one's looking, but its solidity, its position, its very existence as a thing might hinge on the presence of an observer. This isn't just philosophy. Physicists like John Wheeler argued that the universe might be participatory, a self-excited circuit where observation and reality loop back on each other in an endless feedback cycle. But who or what counts as an observer? Does a cat qualify, a bacterium, a quantum detector with no mind at all? Some interpretations suggest that any interaction causing quantum decoherence, any exchange of information, could collapse possibilities into reality. Others insist true observation requires awareness, implying a universe fine-tuned not just for life but for witnesses. This edges uncomfortably close to anthropic principles, where the cosmos seems suspiciously tailored to produce conscious observers like us. Critics dismiss the observers as neo-idealism, a throwback to the old idea that reality is purely mental. They argue that quantum effects are microscopic, vanishing in large systems. Yet supporters counter with deeper questions. Why does the universe appear so finely tuned for complexity? Why does math, a product of human minds, describe the cosmos so perfectly? If consciousness is just a passive spectator, these coincidences strain belief. But if it's a participant, even a co-creator, the fit starts to make sense. Perhaps the most unsettling implication is that consciousness might not be an accident in a material world. It could be the mechanism by which the world materializes. Imagine the universe as a grand symphony where every note hangs in potential until a listener leans in to hear it. The act of observation doesn't just record the music, it brings it into being. Whether the observer is profound truth or elegant illusion, one thing's clear: the boundary between the observer and the observed has never seemed so thin. And if reality truly is a dance between mind and cosmos, we're not just dancing in the dark, we might be holding the only flashlight. The universe as we know it operates by a set of unshakable rules. Matter attracts matter, time flows forward, and particles obey the laws of physics. But what if these rules aren't absolute? What if there's a mirror version of reality where everything is inverted, where matter is antimatter, left is right, and time itself runs backward? This isn't just science fiction. It's a legitimate prediction of CPT symmetry, one of the most fundamental principles in physics, and it might hold the key to some of the cosmos' deepest mysteries. CPT charge, parity, and time symmetry states that if you take any physical process and flip the charge of every particle, mirror its spatial coordinates, and reverse the flow of time, the laws of physics should remain unchanged. It's like a cosmic recipe that still works no matter how you rearrange its ingredients. But here's the twist. While individual flips like just charge or just time sometimes break symmetry, the combination of all three always holds. This suggests an astonishing possibility, a perfect mirror universe, born in the same Big Bang as ours but inverted in every possible way. Picture a world where electrons are positively charged, where galaxies spin backward, and where cause and effect unfold in reverse. To an observer in that universe, we would seem like the bizarre ones, with time flowing the wrong way and matter behaving like antimatter. This mirror cosmos wouldn't just be a curiosity, it could be invisibly shaping our own. Some theorists propose that dark matter, the elusive substance pulling galaxies apart, might actually be the gravitational shadow of this CPT twin, its presence felt but never directly seen. The math is compelling. If the early universe produced equal parts matter and antimatter, as physics demands, then where did all the antimatter go? The mirror universe theory offers an elegant answer: it didn't vanish. It became the foundation of an entire parallel cosmos, forever separated from us by the irreversible arrow of time. In this view, the Big Bang wasn't a single explosion. It was a cosmic fork in the road, birthing two universes back to back like reflections in a double-sided mirror. Could we ever detect this hidden twin? The challenge is monumental but not impossible. Some scientists speculate that certain quantum particles, like neutrinos, might occasionally flicker between the two realities, leaving faint fingerprints in high-energy experiments. Others suggest that gravitational anomalies, unexplained tugs on distant galaxies, could hint at the mirror universe's gravitational influence bleeding into our own. And if the theory holds, it would mean that every star, every planet, even every version of us in that inverted realm isn't just a hypothetical, it's a fundamental part of reality's balance. Of course, skeptics argue that a CPT mirror universe is untestable by definition. If it's perfectly inverted and causally disconnected, how could we ever observe it? Yet the same was once said of black holes and gravitational waves, now cornerstones of modern astrophysics. The universe has a habit of revealing its wildest secrets to those patient enough to look. So the next time you glance at your reflection, consider this. The mirror might not just be showing your opposite. It could be a window into an entire cosmos ticking backward in perfect symmetry with our own. And if that's true, the universe isn't just stranger than we imagine. It's stranger than we can imagine, hiding its true nature in the last place we'd think to look, its own reflection. Imagine a civilization so advanced that it doesn't just inhabit planets, it harnesses entire stars. This is the vision behind Dyson spheres, hypothetical megastructures built around suns to capture their energy output. But what if these weren't isolated feats of engineering? What if galaxies were threaded with countless such constructs, woven into a vast, invisible network powering civilizations beyond our wildest imagination? The implications would rewrite cosmic history, and the eerie silence of the universe might suddenly make sense. The concept traces back to physicist Freeman Dyson, who speculated in the 1960s that any advanced civilization would eventually outgrow its planet's resources. The logical next step, encase their home star in a shell or swarm of orbiting energy collectors, siphoning its power directly. A single Dyson sphere could generate unimaginable energy enough to fuel interstellar travel, supercomputers the size of moons, or even reality-bending experiments. Now picture a galaxy where thousands of stars have been wrapped this way, their light dimmed by the structures soaking up every photon. The night sky wouldn't just twinkle, it would flicker with the shadows of cosmic engineering. Yet here's the paradox. If these networks exist, why haven't we seen them? One possibility is that they're deliberately hidden. Advanced civilizations might cloak their megastructures to avoid detection, whether out of caution or cosmic etiquette. Imagine a universe where the most powerful players stay silent, like hunters in a dark forest. Another explanation is even more humbling. We might be looking for the wrong signals. Dyson spheres wouldn't necessarily blot out starlight entirely. They might irradiate absorbed energy as waste heat, glowing faintly in infrared. Our telescopes have only begun scanning the skies for these thermal fingerprints, and even then, a sophisticated network could be camouflaged as natural cosmic dust or background radiation. Then there's the timeline problem. Civilizations capable of building Dyson spheres might not last long enough to populate a galaxy. They could succumb to war, resource depletion, or technological catastrophe long before their structures become ubiquitous. Or perhaps they transcend physical construction altogether, uploading their consciousness into quantum substrates or higher dimensions, leaving their megastructures as derelict relics. The universe might be littered with the ruins of dead empires, their Dyson spheres gone cold and dark, waiting for someone or something to stumble upon them. But suppose they are out there, humming with activity. A galaxy-spanning Dyson network wouldn't just power civilizations, it would reshape the cosmos itself. Stars shrouded in megastructures would age differently, their energy diverted from natural processes. The abundance of heavy elements, the formation of new planets, even the temperature of interstellar space could be altered by a sprawling energy grid. And if Dyson builders communicate or trade, their network might form a kind of interstellar internet, with energy beams or quantum links threading between stars. The galaxy could already be buzzing with activity, its highways hidden in plain sight. What would it mean if we found one? the discovery of even a single Dyson sphere would confirm that intelligence isn't just possible, it's prolific, capable of bending stars to its will. It would force us to confront our place in a cosmos where someone, somewhere, has already scaled heights we can barely envision. And if they've built this much, what else might they have done? For now, the Dyson Sphere network remains a ghost in the equations, a shadow cast by our own ambitions. But the search continues because if they're real, the universe isn't empty. It's just waiting for us to recognize the signs, and when we do, everything changes. What if the universe isn't just a collection of inert matter and empty space, but a vast, living organism, breathing and self-regulating on scales we can barely comprehend? This is the spine-tingling premise of the cosmic Gaia hypothesis, an audacious extension of the idea that Earth's biosphere acts like a single, self-correcting system. But on a universal scale, the implications are staggering. Galaxies, black holes, even the vacuum itself might be threads in a tapestry of cosmic homeostases, subtly tuned to preserve balance across billions of light years. The original Gaia theory, proposed by James Lovelock in the 1970s, suggested that Earth's biosphere, its oceans, atmosphere, and life, interact like a superorganism, maintaining conditions hospitable to life. Bacteria regulate oxygen, plants modulate temperature, and oceans store carbon in a delicate dance that keeps the planet stable. Now, imagine applying that logic to the cosmos. Could the universe have its own version of planetary homeostases, with dark energy acting like a cosmic thermostat, or black holes serving as gravitational feedback loops? Here's where the science blurs into speculation. Some theorists point to the eerie precision of the universe's constants, the gravitational fine-tuning that allows stars to burn, the cosmological constants' razor-edge balance between expansion and collapse. These aren't just happy accidents, they argue, they're hallmarks of a system that adjusts. For instance, dark energy's mysterious acceleration of universal expansion might not be a passive force. It could be a compensatory mechanism, counteracting gravity's pull to prevent a premature big crunch. Even the distribution of galaxies clustered like neurons in a cosmic brain hints at patterns too intricate to dismiss as random. But how could such a system emerge? One possibility is emergence, the same way ant colonies exhibit collective intelligence without central control. The universe might self-organize through trillions of local interactions. Quantum fluctuations in the early cosmos could have seeded feedback loops where gravity, entropy, and energy flow reached an equilibrium that perpetuates itself. In this view, life isn't an exception. It's a natural outcome of universal self-regulation, a fractal reflection of the cosmos' own stability. Critics, however, dismiss cosmic Gaia as poetic metaphor masquerading as science. Without observable mechanisms, no cosmic cells or detectable feedback signals, the theory risks slipping into mysticism. Yet supporters counter that absence of evidence isn't evidence of absence. Before Lovelock, no one imagined bacteria could alter global climate. Could we be similarly blind to universal-scale biophysics? The most tantalizing question isn't whether the universe is alive in the biological sense, but whether it behaves as if it is. If so, our search for extraterrestrial life might be missing the forest for the trees. The universe itself could be the ultimate organism, and we, along with every star, planet, and atom, might just be its way of understanding itself. So next time you gaze at the night sky, consider this. What looks like chaos might be a dance, one where every element, from the smallest quark to the largest supercluster, plays a part in a symphony we're only beginning to hear. And if that's true, the line between science and wonder might be thinner than we think. What if every moment of your life, every joy, every heartbreak, every breath, has already happened an infinite number of times before and will happen again in exactly the same way forever? No variations, no deviations, just an endless cosmic rerun where the universe repeats itself down to the smallest atom. This is the chilling implication of the time loop universe theory, where reality isn't just cyclical, it's a perfect, unbreakable echo of itself, replaying eternally thanks to a mathematical phenomenon known as Poincaré recurrence. The idea springs from a deceptively simple principle. Given enough time, any system with finite energy and confined to a finite space will eventually return to its initial state. Picture a box filled with gas molecules. Over time, they'll bounce around chaotically, spreading out in what seems like random disorder. But wait long enough, far longer than the current age of the universe, and at some point, all those molecules will, by sheer statistical inevitability, realign into their starting positions. Not just once, but over and over, endlessly. Now apply that to the entire cosmos. If the universe has a finite amount of energy, as our best measurements suggest, and is contained within some boundary, even an expanding one, then given infinite time, every particle, every star, every thought must eventually reconfigure into an exact copy of its past. The Big Bang, it's not just the beginning, it's also the middle and the end and the beginning again. This throws entropy, the universe's inevitable slide toward disorder, into crisis. How can everything reset if entropy only increases? The paradox dissolves when you realize that in an infinitely recurring cosmos, entropy isn't a one-way street, it's a roller coaster. The same math that demands recurrence also ensures that, occasionally, entropy must decrease, like a broken slot machine suddenly spitting out a jackpot. Those rare, statistically inevitable moments of cosmic rewinding are where the universe snaps back to its starting point, erasing all accumulated chaos in one inexplicable, unavoidable reset. But the real gut punch is what this means for free will. If the universe is locked in an infinite loop, every choice you've ever made or will make was predetermined not by fate but by the cold equations of probability. You're not just destined to live your life once, you're doomed to relive it identically, eternally, with no power to change a single detail. The coffee you spilled this morning. It'll spill again in the same way an infinite number of times. The words you're reading right now, you've read them before countless times without ever realizing it. Some physicists argue this is merely a mathematical curiosity, a quirk of statistics with no real-world relevance. After all, the timescales involved are so vast they make the age of the universe seem like a blink. But others counter that infinity leaves no room for irrelevance. If the cosmos truly has no end, then no matter how improbable, every possible state must recur, including this exact one. The time loop universe forces us to confront a haunting question. Is reality a story with infinite retellings, each word unchanged, or is there some escape clause we haven't discovered yet? For now, the math offers no comfort, just the eerie certainty that somewhere, someone, you're already reading this sentence again, and again, and again. What if spacetime isn't a smooth, continuous fabric but something far stranger? A shifting, ever-changing web of connections, like a cosmic game of connect the dots that only appears solid from our limited perspective. This is the radical vision of quantum gravity, a theory that reimagines the universe's very foundation as a dynamic network of relationships where the structure of reality emerges not from geometry, but from the way these quantum links organize and freeze into place. At its core, quantum gravity proposes that spacetime isn't fundamental. Instead, it's an illusion, a low-energy artifact of an underlying quantum graph, a sprawling lattice of nodes and edges where each dot represents a fundamental unit of reality, and each line encodes a possible interaction between them. In this model, the universe begins not with a big bang, but with a frenzied, unstructured soup of these nodes, buzzing with infinite possible connections at ultra-high energies. Then, as the cosmos cools, the graph undergoes a phase transition, like water freezing into ice. Certain connections stabilize, others snap, and from this cosmic crystallization, spacetime as we know it emerges. This phase transition could explain the Big Bang itself. Instead of a singular explosion, it might mark the moment the universe's quantum graph locked in, trading chaotic flexibility for structured rigidity. Picture a molten metal cooling random vibrations give way to ordered crystal lattices. In quantum gravity, spacetime is that crystal, and the Big Bang is simply the moment the cosmic metal solidified. This elegantly sidesteps the singularity problem. No infinite densities, no breakdown of physics, just a natural reorganization of the universe's underlying code. The implications for gravity are even more profound. If spacetime is a graph, then gravity isn't a force bending a pre-existing stage, it's a distortion in the graph structure itself. A black hole, just a region where the nodes are so densely packed that the graph's edges can't escape. Quantum mechanics and relativity, those famously incompatible frameworks, might unify here. The graph's microscopic jitters could give rise to quantum uncertainty, while its large-scale geometry reproduces Einstein's equations. But how could something so abstract ever be tested? Surprisingly, there might be clues in the sky. If spacetime graphited unevenly during its phase transition, it could have left faint topological defects, cosmic cracks where the graph structure didn't align perfectly. These defects might distort light from distant quasars or leave imprints in the cosmic microwave background, like shadows cast by a fractured lens. Some researchers even speculate that quantum gravity could explain dark energy. If the graph's connections continue to evolve, stretching or rewiring over time, it might look like space itself is expanding. Critics argue the theory is too speculative, a mathematical playground without empirical anchors. Yet its elegance is undeniable. By demoting spacetime from fundamental to emergent, quantum gravity offers a universe where the deepest laws aren't about things, but relationships where reality isn't built on space and time, but on the invisible threads stitching them together. And if that's true, the cosmos isn't just stranger than we imagined. It's stranger than we can imagine, a vast, shimmering web where every atom, every star, every thought is just a knot in the grandest tapestry of all. What if the reality we perceive, the solid objects, the predictable laws, the reassuring sense that things are where we see them, is just a surface ripple on a vast, hidden ocean of deeper connections? This is the breathtaking claim of physicist David Bohm's implicate order, a theory that dares to suggest the universe isn't just mysterious, it's fundamentally unfolded, with every part secretly containing the whole in a way that defies all our everyday intuition. Bohm's vision begins with quantum entanglement, that eerie phenomenon where particles instantaneously mirror each other's states across vast distances, as if space and time don't apply to them. Einstein called it spooky action at a distance, but Bohm saw something far more radical, evidence that the separateness we observe is an illusion. In his model, the universe operates like a hologram, not just in the holographic principle's sense of information encoded on boundaries, but in the way every fragment contains the entire image. Break a holographic plate, and each shard still reconstructs the full picture, just with less clarity. Similarly, Bohm proposed that every electron, every galaxy, every thought is a localized expression of a deeper, enfolded reality, where everything is seamlessly interconnected at a level we can't directly perceive. This isn't just poetic metaphor. Bohm's mathematics describe reality as an infinite series of nested waves, a cosmic ocean where what we call particles are merely crests appearing momentarily on the surface, while the true action happens in the depths. Think of a whirlpool in a river. From above, it seems like a distinct object, but dive deeper, and you realize it's just a temporary pattern in the water's flow. In Bohm's universe, everything is like that whirlpool, a transient manifestation of a ceaseless, underlying movement. The implications rewrite our understanding of cause and effect. In the implicate order, events don't happen in isolated chains of action and reaction. Instead, change emerges holistically as the entire system unfolds into new configurations. Picture a dancer whose every move isn't dictated by muscle contractions alone, but by the music, the mood, the space, the whole context. Similarly, an electron's path might not be determined by local forces, but by the universe's total quantum state, a cosmic choreography where every step is entangled with every other. Bohm's ideas resonate strikingly with the holographic principle, where reality is projected from a deeper informational layer. But while holography focuses on encoding, the implicate order adds something profound: meaning. For Bohm, the universe isn't just processing data. It's unfolding meaning through its layers, like a story revealing itself sentence by sentence. Even consciousness, in this view, isn't a byproduct of the brain, but a participatory act in the cosmic unfolding, a process where observer and observed are ultimately one. Critics dismiss the implicate order as metaphysical speculation, arguing it lacks testable predictions, yet its echoes appear in cutting-edge physics. Quantum non-locality, where particles coordinate instantly across space, fits neatly with Bohm's vision of an enfolded whole. Some interpretations of string theory even suggest extra dimensions folded beyond perception, hinting at a hidden architecture beneath spacetime's surface. Perhaps the most haunting question Bohm leaves us with is this: if reality is truly an endless unfolding, what else might be waiting in the depths? The universe we know could be just one note in a symphony too vast to hear, one brushstroke in a canvas too grand to see. And if that's true, the mysteries we chase, dark matter, quantum weirdness, even the nature of time, might not be puzzles to solve, but glimpses of a deeper order, inviting us to look beyond the surface of things. From the holographic universe where reality might just be a cosmic projection, to the chilling dark forest theory that explains the eerie silence of the cosmos, we've journeyed through 30 theories that shatter everything we thought we knew about the hidden structures of existence. These aren't just wild guesses, they're daring ideas backed by equations, observations, and some of the sharpest minds alive, each one pushing the boundaries of what we consider possible. And here's the thing, none of them are about mere matter and energy. They're about the invisible frameworks that might underpin reality, cosmic strings vibrating through the void, entangled particles stitching spacetime together. Even the haunting possibility that our universe is just one layer in an infinite stack of realities. Take the Boltzmann brain paradox, which suggests you could be a fleeting accident of quantum chaos, or the ekpyrotic universe where our cosmic history began not with a bang, but with a collision of higher dimensional membranes. Then there's the simulation argument, forcing us to ask if our lives are just lines of code in some unfathomable supercomputer. And let's not forget the implicate order, where every part of the universe secretly contains the whole, like a single drop of water holding the reflection of the entire ocean. These ideas don't just redefine structure, they dissolve the very categories we use to make sense of existence. So what's next? That's where you come in. Which of these theories rattles your imagination the most? Is it the elegant brutality of the Big Rip tearing spacetime apart atom by atom? The poetic symmetry of the Janus universe where time flows backward in a mirror cosmos? Or something else entirely? Drop your thoughts in the comments, tell us which idea you can't stop turning over in your mind, or better yet, take it further. What hidden truths do you think are still lurking out there, waiting to be uncovered? Because if history's taught us anything, it's that the universe's greatest secrets aren't just stranger than we imagine. They're stranger than we can imagine, and the next big revelation, it might start with a question, maybe even